Hi everyone, and today we will be discussing our second problem in Lagrangian formalism. This is another simpler and most important problem. This is a linear harmonic oscillator problem, and I will be solving this in one dimension, and I will be solving this in cylindrical polar coordinates, right? So in this video, I will be limited up to one dimension, and I will be giving you some homeworks in yeah, two-dimensional and three-dimensional harmonic oscillator, right? So let's solve this problem. Here we have a linear harmonic oscillator, and it's nothing but a spring mass system, and spring is attached to a fixed point O, and M is a mass which is constant throughout the oscillation, and spring has a spring constant of k. It is assumed that the spring is frictionless. Okay, so once we said that we have to write the Lagrangian of the system. Okay, since it's a one-dimensional harmonic oscillator, I am taking this as a x direction, and L is nothing but T minus V. T is the kinetic energy and V is the potential energy, and T is nothing but, since it is in x direction, I can write T is equal to of mx dot square, right? And for this kind of spring mass system, with the help of Hooke's law, we can write F is equal to minus kx. Once we have the force, we can write the potential with the help of this form. Force is nothing but the negative gradient of the potential. So with the help of this, we can write potential is equal to of kx square. Potential is nothing but of kx square, right? And once we write this Lagrangian, L is equal to of mx dot square and minus of kx square. Here in this problem, you can observe the generalized coordinate is x. Okay, so there is no other coordinate involved. So because the displacement is in only one direction, which is nothing but x, so we fixed this as x, right? Okay. Now we have this Lagrangian. With the help of Euler-Lagrange's equation, we can write the equation of motion, right? So for the generalized coordinate x, we'll be writing Euler-Lagrange's equation, which is nothing but d by dt of dou L by dou x dot minus dou L by dou x equal to 0, right? So we have to find dou L by dou x dot, which is equivalent to x dot is nothing but, so once you differentiate this term, because this term only consists of x dot here, so we will be getting mx dot. Okay, and we have to find d by dt of dou L by dou x dot. So d by dt of dou L by dou x dot, which is nothing but d by dt of mx dot. M is the constant, so we need not to differentiate that. So we can write this as mx double dot. And second term we have dou L by dou x. So once we differentiate the second part, so we will be getting minus minus kx square. Here we have minus kx square, right? So once we have this, we can substitute these values, that is mx double dot and minus kx square instead of these two terms, right? So we can write mx double dot minus into minus kx square. So this is x here, this is not kx square, this is minus kx here. So we can write minus kx equal to 0. So mx double dot plus kx equal to 0. On rearranging these terms, we will be getting x double dot plus k by m x equal to 0. This is the equation of motion of a linear harmonic oscillator in one dimensions. Right. So I'll be giving you some